Welcome back, AP Calc friends. This is section 4.9, Day 1 notes. So today we are going to focus our conversation on antiderivatives. This is a word that has already come up this year. In fact, we learned about antiderivatives a little bit in section 2.8 and 2.10 back in chapter 2, when we were kind of learning the characteristics and the relationships between f of x, f prime of x, and f prime prime of x, and kind of going forward and backward based on graphs, based on knowing information about increasing, decreasing, concavity, and such. So I guess it makes sense that sometimes we have a function and it would be nice to know information about the function that it came from, right? So in that case, we would call that function its antiderivative. One specific example would be if we had a vehicle's velocity and we wanted to know its position, we would need its antiderivative because we know velocity is the derivative of position. Therefore, position would be the antiderivative of velocity. So our working definition here for an antiderivative is a function f is called an antiderivative of little f on an interval I if big F prime of x is equal to little f of x, right? If the derivative of the antiderivative is equal to the function, then we would say that that was an antiderivative of the function. And so again, recall from chapter 2 that we've already learned how to use the characteristics of a graph to sketch its derivative, but the problem is when we're going backwards, what we don't know is the constant term that we could possibly have, right? Because we know that when we take the derivative of a constant term, it goes to 0. So if we're going backwards, we know that our antiderivative could possibly have a constant term that went to 0, and we don't know what it was. So that's why there's always some ambiguity when you're going backwards, when you're trying to go from like f prime to f, when we don't know exactly where our y values should be unless we have an initial condition that we're given. And so this phenomenon or this issue with going backwards and not knowing the constant term of the antiderivative, we call this the plus c, okay? The plus c. And so we have another theorem here. If capital F is an antiderivative of little f on an interval I, then the most general antiderivative of f on the interval I is capital F of x plus c, where c is some arbitrary constant. And we don't know what it is unless we have information that allows us to solve for it. And we will get to examples like that, and then you'll understand better what I'm talking about. So here you can see we have this lovely picture of this family of graphs where it says all of the graphs on the left represent the family of antiderivatives for the function little f of x equals x squared. Because we know that if x squared is a function and we want its antiderivative, then its antiderivative should be a cubic function. Therefore, the entire family of antiderivatives look like snakes of the form y equals x cubed. But the problem is it could be x cubed plus 0, it could be x cubed plus 2, it could be x cubed minus 5. All of those would have a derivative that would be of the type x squared. And so without knowing that, we really can't figure out exactly what our antiderivative is exactly. So that's why we would say there's plus c, because without knowing an initial condition to help us solve for the constant term, there are an infinite number of antiderivative possibilities there that could all fit, the x squared. It could be, 1/3 x cubed plus or minus any value. So let's talk for a second about all of the derivatives that we already know. And if we are now thinking in terms of antiderivatives, we just have to work backwards instead of forwards. Okay, so another opportunity for you to perhaps make some flashcards and start thinking about the derivatives the functions that they came from, and are you just as comfortable moving backwards in that relationship as you are moving forwards? Because when we're finding antiderivatives, we're thinking in reverse. All right, so again, I would say make some flashcards of the derivatives in this table. Basically, our basics like natural log, e, sine, cosine, tangent, secant, cotangent, and then our inverse trig functions as well, because those come up sometimes too. All right, so let's try some examples of finding antiderivatives. Now, in the first few examples here, example 1, part A and part B, it says find the most general antiderivatives of the following functions. So what those words right there mean, because they haven't given us any initial condition to allow us to solve for C. So basically this means don't forget the plus C. Okay, don't forget the plus C. All right, now this is the first time we're ever trying to create an antiderivative equation, so let's take our time. All right, now we know that instead of subtracting exponents, we're going to be adding exponents because we're going backwards, right? And we also know that whatever exponent that we are adding, we have to undo it with a coefficient in the front. For example, if we have an x squared and we're changing it to an x cubed, then we need to put a 1/3 in front of our term so that if we were to differentiate, 3 times 1/3 would undo itself, okay? Because you can always check your work with antiderivatives. If you take the derivative of your antiderivative, you should be able to get back to the function that you started with. And if you don't, then you know that you have some sort of an error that you have to fix. All right, so let's look at letter A. If my little f of x has 3 terms, then my big f of x, my antiderivative, should have 3 terms plus the constant term plus c. All right, so if 1/2 is the term in f of x, then the term that it came from had to have been 1/2 x, right? Because if you take the derivative of 1/2 x, you get 1/2. So check it as you go. My second term was x squared. So I know that the antiderivatives term has to be an x cubed, but because of that, I'm going to have to multiply by 1/3 to undo that, and then the coefficient that was already there, the 3/4, that stays as well. Okay, so now check it. If I were to differentiate this term, I would bring the 3 down, but 3 times 1/3 would cancel. I'd still have 3/4 x squared, which is exactly the term that I started with. So then I know it's correct. Now in the next step, I will simplify it. And then my last term, I have an x cubed, so I know that my x cubed is going to become x to the 4th. And since it's going to become x to the 4th, I know that I'm going to need a 1/4 in front of my term to undo it. But then I also need the coefficient that was already there, which was -4/5. So again, let's check it. If I were to differentiate the term that I just created, I would bring the 4 down. The 4 and the 1/4 would cancel out or become a 1, times the -4/5 would be -4/5 x, and then it would be cubed, which is exactly what I started with. And then of course I need my plus c, because perhaps there was a constant term that I took the derivative of that went to 0. We don't know. So now let's clean this up. My final answer is going to be f of x equals 1/2 x plus 3/4 times 1/3, that just makes 1/4 x cubed, and -4/5 times 1/4 makes -1/5 x to the 4th plus c. Let's take a look at letter B. Letter B is giving us some terms in radical form. So it would be a lot easier for us if we first rewrite our polynomial in exponent form. So the 4th root of x cubed, that is going to be x to the 3/4 power. And the 3rd root of x to the 4th, that is going to be x to the 4/3 power. That's a little bit confusing because those exponents are reciprocals of each other, so just be careful here. So again, I am going to be adding 1, right? So now capital F. If I'm adding 1 to 3/4, then I'm adding 4/4 to 3/4. 4/4 plus 3/4 would make this term x to the 7/4. But again, I have to undo that by multiplying by the reciprocal of my exponent, so I have to put a 4/7 in front of my term. And then the same thing goes for the next term. I have 4/3. If I want to add 1 to 4/3, I'm going to be adding 3/3 to 4/3, which is going to make this 7/3. And I need to undo that with the reciprocal in front, 3/7. Okay, so now before we turn this back into radical form, oh, and of course, sorry, I need my plus C. Before we turn this back into radical form for our final answer, let's check. If I were to differentiate the first term, I'd bring down the 7/4. 7/4 times 4/7 would make a coefficient of 1. And then if I subtracted 1 from 7/4, I'd be taking away 4/4, which would leave me with x to the 3/4. So the first term is correct. The second term, if I brought down the 7/3, 7/3 times 3/7 makes 1. And then if I subtracted 3/3 from 7/3, it would be x to the 4/3. And then if I took the derivative of c, which is just some number, it would go to 0. All right, so you could either leave your answer in the fraction exponent form, or if you wanted to, you could rewrite this in radical form. So this would be 4/4 roots of x to the 7th over 7, which certainly we could pull some x's out, but we're not going to bother with that right now. And 3 cube roots of x to the 7th over 7 plus c. So either one of those is correct, but to be honest, my preference would probably be this one, just because it's a little cleaner. Example 2 asks us to find the antiderivative, big capital F, of little f that satisfies the given condition. So now they're giving us something that will help us figure out what c is supposed to be. And then they want us to compare the graphs of little f and big F to check our work and make sure that things like turning points align with x-intercepts and increasing, decreasing aligns with above the x-axis, below the x-axis, all the things that we know about a function and its derivative. All right, so our first job here is going to be to write a generic equation for the antiderivative of f of x, little f. So capital F of x is going to be, again, one term at a time. So the x to the 4th I know is going to become x to the 5th, but then I'm going to have to undo that by multiplying by the reciprocal of 5, which is 1/5, but don't forget the coefficient that was already there. And then my second term is going to become x to the 6th, so I have to put a 1/6 in front of the term, but don't forget the coefficient that was already there. And then I know I have a plus c. So let's simplify and check first, and then we'll solve for c. So my capital F of x is going to be 5 times 1/5 is just 1, so I get x to the 5th. And then negative 2 times 1/6, that's going to be negative 1/3 x to the 6th plus c. So if I differentiate x to the 5th, I get 5x to the 4th. That was the first term in little f of x. If I differentiate negative 1/3 x to the 6th, I'd bring down the 6. Negative 6 over 3 would be negative 2 x to the 5th, which is the second term in the polynomial that I started with. So now f of 0 equals 4. So now we're going to use that. To find our c value. So when we plug in 0 for x, so 0 to the 5th minus 1/3 times 0 to the 6th plus c, that is equal to 4. Well, anything to the 0 power is 0, so basically this term cancels and this term cancels, and we find out that our c value is 4. So that tells us that our exact antiderivative is x to the 5th minus 1/3 x to the 6th plus 4. Okay, so here's our capital F of x, and back at the beginning of the problem we were given our little f of x. And so now our job is to graph both of these, and we're just going to use our graphing calculator, and we're going to look at the graphs and we're going to compare what's going on and make sure that our work that we did is good work and that our answers make sense. let's see, I want my antiderivative to be purple. So I'm actually going to, based on the colors on my paper, so I'm going to put that in y4. That's kind of a, it's pinkish, but it's close enough to purple here. So x to the 5th minus 1/3. So I'm going to put 1 divided by 3 in parentheses. Whoops, missed the 1 there. X to the 6th. And then plus 4. Okay, and then my little f of x was green, so I'll put that in y5, and that was 5x to the 4th minus 2x to the 5th. There we go, minus 2x to the 5th. There we go. And I'm just going to start with a zoom 6 to begin with because I'm not sure what I need. So there's my antiderivative, my capital F. And there's my little f. Okay, so obviously I can tighten up my x-axis, but I need to go taller on my y-axis. So I'm going to change my window here. Y-min, I'll just go with like a -5 on that. And then y maximum, I'm not sure. Maybe I'll go to like 25. And then, oh goodness, sorry. That's what I wanted for my y's. My apologies. So I'm going to put -5 here, and I'm going to put 25 here for my y's. And then I'm going to go back up to my x's, and I think I can just do like a -5 to 5 on the x-axis here, because it wasn't very wide. Okay, now let's take a look at what we have. So again, there's our antiderivative, our capital F, and there's our little f. Okay, so when we look at this, we're looking for things like if the green graph is supposed to be the derivative of the purple graph, then where the purple graph is increasing, the green graph should be above the x-axis. Well, if you look at this picture, the purple graph is increasing from here to here. Green graph is above the x-axis. Then I have this sort of horizontal line here where it's on the x-axis. That makes sense. Slope is 0, value is 0. But then it's increasing again all the way to here, where my green graph is above the x-axis all the way to there where we line up with that maximum. And then where my purple graph starts to decrease, that's where my green graph crosses the x-axis and begins to decrease. Okay? So, or begins to become negative or drop below the x-axis. So this looks exactly like it should look in terms of a function and its derivative. So now let's go back to our paper and let's just sketch what this looked like on our paper. And these are by 5s. So my capital F of x, and again, this is a loose drawing here, so don't, something like this. It looked something like that. And then my green graph, its derivative, that one, or this was supposed to be a little more flat there in the middle. Sorry about that, but then we've got, looks something like that. And you can certainly take the time to do a little bit better job on your paper, but here's my f of x. And here's my capital F of x. Okay, so that's the end of example number 2. Our final example, example number 3, it says find f, and they give us an equation for f prime prime. So they are asking us to go back 2 functions, right? If we have a second derivative and we want the original function, then we have to find 2 antiderivatives. First we have to find f prime, then we have to find f. And they've given us 2 pieces of information to help us, that f of 4 is 20 and f prime of 4 is 7. So that's going to help us with those plus c's, with those initial conditions. Okay, so let's start by writing our given function as a variable with an exponent in the numerator instead of as a radical in the denominator. So f prime prime of t, I'm going to rewrite as 3t to the negative 1/2 power. All right, so then my first antiderivative would be f prime of t, right, going backwards 1. And so I'm going to do the same thing. I'm going to add 1 to my exponent. So adding 1 to negative 1/2 is going to make this t to the positive 1/2. But then I have to undo that by multiplying by the reciprocal of that, which is 2 over 1. And the coefficient that was there is still there. Okay? And then I have my plus c. So when I simplify this, my f prime of t is going to be 6t to the 1/2 plus c. Now, before we solve for c, let's check it. If we were to differentiate 6t to the 1/2, we would bring down the 1/2. Half of 6 would be 3. That would be our coefficient. And then if we subtracted 1/2, or sorry, if we subtracted 1 from 1/2, we'd have negative 1/2. So it would be 3t to the negative 1/2, which is what we started with. So we're good. So now we're going to solve for c. And we're going to use the fact that f prime of 4 equals 7. Right? So if f prime of 4 is 7, then 7 should be equal to 6 times 4 to the 1/2 power plus c. I'm just plugging in 4 for t, and the result of that should give me 7. And that allows me to solve for c. 4 to the 1/2 power, square root of 4, that's 2. 2 times 6 is 12, so I get 7 equals 12 plus c. If I subtract 12 from both sides, that tells me that c is negative 5. So that tells me that my f prime of t is 6t to the 1/2 power minus 5. But now I have to do it one more time. Now I have to find another antiderivative. So f of t would be the antiderivative of that. So same process. If I have t to the 1/2 and I add 1, that's going to become t to the 3/2. But then I have to multiply in front by the 2/3 to undo it. Plus I already had the 6 there. The negative 5 is going to become negative 5t. And then I have that ambiguous constant term, which we would call our plus c. So now let's check before we solve for c. If I were to bring down the 3/2 power, 3/2 times 2/3 makes 1, and 1 times 6 is 6. So the coefficient is 6, and then 3/2 minus 1 would be t to the 1/2 power. 6t to the 1/2 power is the term I started with. If I differentiate negative 5t, I would get negative 5, which is the second term I started with. And if I differentiate plus c, that would go to 0. All right, so now I need to solve for c. And again, I'm going to do that using the fact that f of 4 equals 20, right? That was given to me. So 20 should be equal to what I get when I plug 4 in. Oh, and I can simplify, by the way. 6 times 2 is 12, divided by 3 is 4. So 4 times 4 to the 3/2 power minus 5 times 4 plus c. All right, 4 to the 3/2 power. That's the square root of 4, which is 2. And then 2 cubed is 8. And 8 times 4 is 32. So I get 20 equals 32 minus 5 times 4 is 20 plus c. 32 minus 20 is 12. So 20 equals 12 plus c. If I subtract 12 from both sides, I get c is equal to 8. So then my f of t is going to be equal to 4t to the 3/2 power minus 5t plus my constant term, which I just found to be 8. So there's an example where we found not one, but two antiderivatives given initial conditions that allowed us to find the plus c values.